Hey everyone, welcome to our final video of this series. Now, this video, we are going to be talking about what we call bearings. And this is one of the actual big real world applications of trigonometry, as well as angle geometry, which we've done in previous years. And it's bringing together a lot of these concepts we've talked about, both in trigonometry as well as angle geometry. And what this tells us is bearings are all about direction. So if you remember back in, I did this about as early as elementary school, maybe some of you have done it a little more recently, but if we remember our compass directions here, we have the directions of north, east, south, and west. And all of these directions, although we know them, we know the names of them and roughly how that looks, we haven't yet considered all of the different angles that live within this. Now, from north to east, if you look at how these two lines meet, even though I haven't drawn them very well, these look like they are perpendicular. So they're meeting at 90 degrees here. So between north and east, we have 90 degrees. Now, what about from north to south? If we go all the way from north to south, it looks like we're going straight down pretty much, because north and south lie on the same line. So we can say the angle between north and south is going to be a 180 degree angle. Or another way we can think about this is that there is also another 90 degrees between east and south, and then 90 plus 90 gives me 180. Looking ahead here, we're starting at 180 and we're going another 90 degrees between south and west. So if we were to keep drawing a line across here, so let's say an angle here, we have gone 180 degrees plus 90 degrees. So that gets us to 270 degrees. And finally, getting back to north means a full revolution. So based on our angle relationships we did a while back, we see that anytime we make a full circle or a full revolution and end up at the same place, we have traveled 360 degrees. So bearings are all about giving us directions. Now, we can define a bearing as, so we have here bearings are, or we'll say a bearing. So a bearing is an angle measured clockwise from north. Clockwise from north. So we were dealing with a lot of these angles as we kind of traversed through our northeast southwest here. So all the way through this revolution here, we see a bunch of little angles popping up. And whichever way we travel from the perspective of north, that is going to be what we call a bearing. So if you're walking on a bearing of 30 degrees, for example, that tells you some kind of direction you're walking, and we're always looking from the perspective of north. Now, we typically write bearings as 3-digit numbers in terms of our angles. So examples of bearings include, for example, 008. This means we've gone 8 degrees, or maybe 042 degrees. That's 42 degrees. Or we can go, I don't know, 189 degrees. So we're using 3 digits because our biggest angle bearing is going to be 360 degrees, and there are 360 there are 3 digits in the number 360. That's really why we use these. So going straight into a question here, we've defined bearings as some kind of direction from north. So here, our perspective matters, and we're going to see this in this particular question. So here, from the diagram shown, give the bearing of A from O. So we're looking at the final position A, this red dot here, from the starting position of O. Now, in this particular question, we are actually given a number. So here, this angle, I can see I have an angle of 120 degrees. So we start, here we have A from O. So we're going to start at this O, look at the north direction in relation to O, so up here, and we are going to observe this angle here. So we're actually going to be making an angle here. So we have this blue line and this blue line here. So we're looking for the angle inside, which is 120 degrees. So, and we can see that because it's an obtuse angle. It's between 90 and 180. So looking at A from O gives us an angle of 120. So let's write that here. So A is going to be 120 degrees here. Now this is where it gets a little bit tricky, right? We are asked now to give a bearing of O from A. So we've changed the order around. So what I'm going to do, I'm going to draw this a little bit bigger down here, just so we can read it off a little bit easier. So we have our northeast, southwest here, and I have O going down to A here. Let's just write these in, north, east, south, west. I have my O here, and I have my A here. Okay, now, this time we want to find the location of O, an angle direction, from the perspective of A. So we're always measuring bearings from the perspective of north. So I'm going to draw in another northeast, southwest map from the perspective of A. Because I'm measuring O's position from A. So from the perspective of north up here. So the angles I'm counting are going to be a little bit different here. So I'm going to write here northeast, southwest. Now, remember how we defined this? We defined a bearing as an angle measured clockwise from north. So from north here, I'm not looking at the angle over here because that is in a counterclockwise direction. I'm trying to measure this entire angle here. Because once I've drawn the line from O to A, I have to get to an angle that meets back at this line pointing back in the direction of O. So now I kind of want to count my angles here. So there's a couple of ways we can do this. Now, I'm going to introduce you to both here, and this is where our angle geometry really comes into play. Because notice that whether I'm in the north direction here or here, north is always constant. So anytime I'm facing that direction, I can say that I have parallel lines. Now, if this entire angle is 120, and this guy here is a right angle, what's going to be the angle value of this tiny angle here? Well, to find that, I want to find the difference between 120 and 90. So minusing one from the other, that gives me an angle in here of 30 degrees. But now check this out. Our norths are parallel together, are parallel to one another. Our easts are also parallel to one another. So both the vertical direction and the horizontal directions, because north, east, south, west, those directions are always constant, we can say that we have some parallel lines happening. So if we look at this angle 30, let's notice how we can relate it to this angle in here. Now, if we sketch along these lines, we see the letter Z being formed. So when have we seen something like that before? We saw this in angle relationships. These two here are what we call alternate angles. And if we remember from angle geometry, alternate angles are always equal. So therefore, if that angle is 30, this angle in here is going to be 30 as well. Now I can count up all of these angles now. I have 90 degrees from here to here. I have 180 degrees down to here. I have 270 degrees here, and then I have another 30 degrees. So adding all those up, the bearing, well, I'll do it up here. The bearing of O from A is going to be 270. This one from north to west, that's 270 degrees. Let's write that in. Plus another 30 degrees. And that's going to give me 300 degrees. Now, another thing we could have done is we could have said that, well, if we consider this angle 120 and map it with this, I have this C shape. So my 120 and this angle in here, let's do the color red, these are co-interior angles. So they add up to 180. So this angle is going to be 60. And we could have also taken 360 degrees, a full revolution, minus my 60 here, which would have given me 300 also. But that is how we can start to recognize our directionality here. And where and how that matters. How two things that sound very similar, O to A, or O from A, and A from O, sound quite similar, but the answer we get is going to be very different. Now let's look at our second question here. And here is where we're going to start applying not only our angle geometry, but also our trigonometry that we've done so far. Now we want to underline the most important bits here. So a bushwalker walks 3 kilometers on a bearing of 60 degrees from point A to point B. So that is this line up here. This is the direction and the distance the bushwalker is walking. How far east, correct to 1 decimal place, is point B from point A? Now, let me draw this a little bit bigger. I'm only working in this little quadrant up the top, so I'm just going to draw that one there. So I have my north, I have my east, and I have the distance my bushwalker has walked. That's 3 kilometers. And it's on a bearing of 60 degrees. So this angle here, let's do that in a different color. This angle is 60 degrees. And now I'm being asked how far east, correct to one decimal place is point B from point A. So I have here A and B. And I'm looking at how far east. So what this particular length is going to be. Now, if I draw a perfectly horizontal line from going from right to left, now this is east, the angle it makes with north is going to be a 90-degree angle. Because remember, the north direction is always perpendicular with the east direction. It always makes a 90-degree angle. So, now that we've drawn this, we notice that this is kind of just a trigonometry question. We're looking at how far east this is, but we can construct a triangle out of all of these directions. I've got my original distance walked, I've got my A to north, and I've got my point B, its east direction from my north here. So I'm making a triangle here. So if I actually do this, we can see that, well, my distance east, let's call that D, kilometers. Now we are using our right angle trigonometry, because what side is this 3 kilometers in our triangle? Well, it is the side opposite to our right angle. So it's the biggest side. This is the hypotenuse. And the side D we're after is going to be, you can see here, it's opposite to my 60 degrees. It is the side opposite to my angle in question, the angle I've been given. So, remembering our SOHCAHTOA, we can select the appropriate trigonometric ratio to use here. Now we have an opposite and a hypotenuse, so we are going to use sine here. So that means that, to show my working out, I'm saying that my sine from the perspective of this angle of 60 degrees equals to my opposite over my hypotenuse. Well, my opposite's going to be D, my hypotenuse is going to be 3. And now it's a matter of solving the equation. So I want to undo this D dividing by 3 because I want to slowly get to finding out what D actually is. So here D is getting divided by 3 to give me sine of 60. So I'm going to do the opposite operation. I'm going to times both sides by 3. So that means that 3 times sine 60 equals to my side D. And when I pop this to my calculator and round this to one decimal place, I'm going to get the length of D being 2.6 kilometers here. So that means my point B is 2.6 kilometers east of my point A. Now we could have either done it like that, or we can also see that, well, my B, I can draw it down to here, and we're just looking at where B is in line vertically. How far is that from my point A? That's what we're trying to find here. So you could have constructed this type of triangle, or you could have gone with the one that I went to. You're going to get the same answer every single time. But we are, like we did when we previously applied trigonometry, we were constructing triangles. We were making these triangles as models to actually calculate different types of lengths here. So let's do a quick sense check. Our answer, 2.6 kilometers, that is shorter than 3 kilometers. So that makes sense as an answer. 3 is our hypotenuse, so it's the longest side. If we got an answer bigger than 3, then we know we've done something wrong. All right, very last question. This is going to be a little bit trickier and a bit wordier, but let's have a go at it together. Now we have a fishing boat sails from point O and sails 75 kilometers on a bearing of 160 degrees to point B. How far east to the nearest kilometer of its starting point is the boat? So how far east have we traveled? And what is the bearing of O from B? Now, quite wordy, there's a lot to do here, but if we draw this up, let me just do this here. So if we have north, south, and I have my point O here, and I have my point B, I've traveled 75 kilometers, and I have east in this direction, and an angle of 160 degrees. I want to find how far east I am from this point B to my starting point O. So I can just draw a horizontal line and see, well, when do I have to stop? Well, I have to stop at this point here because that's in line vertically with my O. So I have my distance, my east distance of B to O, let's call that D. I have my 75 kilometers that this has traveled, and I also have this outside angle of 160 degrees. Now, we are asked to find D, and we have a right angle triangle because once again, the east direction is always perpendicular to the north direction. We have a right angle triangle. Let me actually draw it here. We have 75 kilometers, we have D, we have a right angle. But what's this angle in here going to be? Or this guy here? Well, I know that from north to south, that is going to be an angle on a straight line. So that is an angle size of 180 degrees. And this little bit here makes up the distance between 160 degrees, or the difference between 160 and 180. So if I subtract one from the other, so subtracting 160 from 180, I'm going to get 20 degrees over here. So now I just have a simple right angle triangle question. These ones in trigonometry that we've been doing so far leading up to this moment. Now, it's just a matter now of solving. So once again, we're just going to label all of the sides. Now my 75 is opposite to my right angle, so that's going to be the hypotenuse, and my D is opposite to the angle here. So that is going to be my opposite side. And once again, I have an opposite and a hypotenuse. So katoa tells me I'm going to use sine. So that means that the sine from the perspective of my angle 20 degrees is going to be my opposite D over my hypotenuse 75. And this becomes really similar because I just want to solve the equation in the same way. So I'm going to multiply both sides by 75 because I want to undo this division of 75. And then I'm going to find that D equals 75 times sine of 20. And we're looking at the nearest kilometer here. So when we put this in our calculator, we're going to get 25.651, etc. So my D is going to be equal to roughly 26 kilometers to the nearest. Then this is it rounded to the nearest kilometer, to the nearest whole number. So that's the first part, right? We've shown all of the information on the diagram, and I want to preface everything that we're doing here by saying that if you draw a nice picture, it's going to make your life so much easier. So anytime you get something like this, if you've drawn it nicely, you should clearly see a triangle. And what I like to do is I even draw the triangle here separately, so it becomes an easy trigonometry question that I'm already used to trying to solve. And so it becomes the same one that we've been doing all the way up until now. So that is part A. Now part B asks us, what is the bearing of O from B? So I'm going to draw this diagram again. So I have, and when you're doing these, it helps to like draw it really big, because the bigger it is, the clearer it's going to be, and just the nicer it's going to look in general. So I have my north, east, south, west. I have my point B. I have an angle here of, what was it, 160. And I have 75 kilometers here. And I want to draw up now another set of northeast, southwest axes from B. Why? Because now we're finding the distance from, well, the bearing of O from B. So we're looking from the perspective of B. So I want to get a feel for where north is in relation to B. This is going to make our lives a lot easier. South and west. Okay, now, once again, I can do this in a number of different ways. So, just to know exactly how we want to approach this question and sort of what angle we're actually looking for in general, I want to look from the perspective of north from B and then figure out how many what the angle size is going in the clockwise direction before I get in line with this line stretching from B to O. So that is my unknown angle, and that's going to be the bearing I'm going to want to find. Now, I'm going to do this question in a slightly different way to the previous one, because it's actually a very similar question. Now, if I draw up this thing here, remember, all norths are parallel. So whether I'm standing north here, a certain distance away on my left-hand side, on my left-hand side, that's going to be the same direction as north on the right-hand side, because all north directions are constant. So they're always going to be, no matter how far you stand away from someone, if you're both facing north, your directions are going to be parallel to one another. So now we have this thing here. Now we want to find the angle relationship. So here I make this C shape. So I'm looking for co-interior angles. And these add up to 180 degrees. So that means that this angle here, 160, as well as this angle down here, have to add up to 180. Now, what number do I have to add to 160 to get me to 180? Well, that's just going to be 20 degrees here. So, if that angle is 20 degrees, I want to find what this guy is. Now, if a full revolution is 360 degrees, so let's do that in color purple. So if an entire revolution here is 360 degrees, then my bearing is just going to be the difference between 360 and 20 degrees. So my bearing of O from B equals 360 minus 20 degrees, which gives me 340 degrees. And we could have found this angle of 20 in a variety of different ways. If we clear this up, you could have also seen that what we established before, this angle is 20 degrees from up here because of our angles on a straight line. And also we could have said, well, we have an alternate angle going on here. So these angles are going to be equal. So I get 20 equal to 20. Now, it doesn't matter which way you choose to go about this, as long as you are just picking the right angle relationship. Especially when we deal with bearings, the most important thing is our perspective. So are we looking at O from the perspective of B, or are we looking at B from the perspective of O? And those perspectives always go clockwise from north. So as long as we have those nicely laid out, we've got a good drawing, and we use our angle relationships correctly and trigonometry when we require it, these questions end up becoming a lot easier. But this brings us to the end of our topic. Thank you so much for joining me, and I'll see you in the next one.